Okay, thank you. Today I'll be discussing a comparison of the polar volatiles that we see on both Moon and Mercury, and hope to provide an overview that will lead into the following parallel session in the side room, which is focused on volatiles in the solar system. And as we said, I'm presenting some reviews of the discussions and talks that occurred at Microsymposium 57 this spring, where we discussed just these themes, polar volatiles on Moon and Mercury. And before I begin, I'd like to give a special thanks to Dave Lawrence, who provided a synthesis talk at Micro and allowed us to draw from some of those summary slides today. So today I'll be discussing different lines of evidence we have supporting that the poles of Mercury and the Moon are occupied by water ice deposits. Specifically, we'll be looking at the permanently shadowed environments that are of cold enough temperatures to sustain water ice, different Earth-based and orbit-based radar measurements of the poles, hydrogen measurements that were detected from orbit, as well as the topography of the poles and derived temperatures, and finally, different reflectance measurements that have occurred at the poles. And then I'm going to conclude with a discussion of possible explanations that have been invoked to rectify some of the differences we see on Mercury versus the Moon. So discussing water ice on the Moon and Mercury is a very exciting topic, and it's not always an intuitive one for the public, specifically with Mercury given its proximity to the Sun. But as we know, both Mercury and the Moon are airless bodies, and so they lack any appreciable atmosphere that could help trap heat. And also, Mercury and the Moon have very low obliquities, and so you get these regions at the poles where you don't have the Sun striking directly on the surface. And in fact, especially when you're in a deep impact crater, you get these regions that are called permanently shadowed regions, or PSRs. And both the Moon and Mercury have PSRs. So on the left of the screen is a map of the North Polar region we put together for Mercury, where we've highlighted all the regions that are in permanent shadow in blue that we've derived from the topography of the planet. And on the right is a map of the North Polar region of the Moon, where Irwan did the same thing, where the permanently shadowed regions are highlighted in red. So both bodies have these PSRs, and they're of cryogenic temperatures that are cold enough to trap volatiles within them. And these volatiles are very significant scientific resources. They represent these accessible storehouses that will allow us to understand planetary formation and evolution and how volatiles have evolved throughout the history of the inner solar system. And volatiles also represent an important resource when thinking about future exploration and furthering human autonomy in space. So our first looks into these permanently shadowed regions come from the Earth-based and orbit-based radar measurements on Moon and Mercury. So for Mercury, these start back in the early 90s with imaging campaigns both at the Goldstone and Arecibo observatories. And so these are two images taken from two different observation dates of the North Polar region of Mercury at Goldstone. And in the white, we're highlighting radar enhancements that are showing that the poles of Mercury are consistent with having water ice. And with a repeated imaging campaign that took place at Arecibo in the late 90s, we were able to dilute these images into these very clear, extensive radar bright deposits on the surface of Mercury. And these extensive, pure radar bright deposits align a one-to-one correlation with the permanently shadowed regions that we've mapped on the surface. For the Moon, the story is not as clear. The first bistatic radar measurements were taken with the Clementine mission, and they indicated hints of water at the south pole of the Moon. So this is a figure where we're looking at a circular polarization ratio on the y-axis and your bistatic angle on the x-axis. And essentially to identify cold trapped volatiles, whether it's ice or another volatile, you want a high ratio as your beta angle approaches 0. And so what we saw is we got enhancement at one of the orbits taken at Clementine, but we didn't get this enhancement visible in all of the orbits. Future missions also had different bistatic and radar measurements, and these indicated that there are regions at both poles on the moon that are indicative of water ice. There are some ambiguities that still exist with this data, though, specifically when thinking about surface roughness and how this plays into a high circular polarization ratio. But there are anomalous craters, which are mapped here in the green circles, that have high circular polarization ratios confined within the craters that correlate with your regions of permanent shadow. And so for conclusion, for the radar-based measurements, both bodies show evidence of high circular polarization ratios, although on Mercury, they're much purer measurements and a bit more extensive. Furthermore, we also have hydrogen concentrations that have been detected from orbit for both bodies. So on Mercury, this is mostly work done by Dave Lawrence, working with the neutron spectrometer on MESSENGER. So on the x-axis here, you have the relative epithermal neutron count, and on the y-axis, we're increasing in latitude from 30 degrees to the pole. And this blue line is representing the theoretical count that you would get if you had pure water ice occupying all of the permanently shadowed regions on Mercury. And the MESSENGER data is overlying this in red, and what you see is that it's almost an exact correlation, which indicated we had this broad spatial suppression of the hydrogen at the poles of Mercury in these permanently shadowed regions. On the moon, as Matt talked about earlier, for those of you who saw his talk, the enhancements aren't as homogeneous, and they're not centered at the poles of the moon today. And they also are suggestive of some sort of layering of the deposits. So while both the moon and Mercury have measurements of hydrogen detected, they're much more pure for what we see on the surface of Mercury than they are on the moon. We also have temperatures that have been calculated from the topography measured for each planet, and this is mostly work done by Dave Page. So for Mercury, this is a map of the North Pole where they've derived biannual maximum temperature from the topography of the planet. And what they found is that there are locations in the permanently shadowed regions on Mercury that are of cold enough temperatures to sustain stable water ice on geologic timescales. However, the ice has to be insulated by a thin layer of something else, approximately 10 to 20 centimeters thick, which is suggested to be an organic-rich volatile. There is one exception to this, and that's Procovia Crater, which you can see over here, which has water ice exposed on the surface of Mercury. And Dave has completed the same thing for the moon as well, where we also saw that there are these extensive regions on both the subsurface and the subsurface of the moon that are able to host water ice on geologic timescales. And then finally, we have reflectance measurements for the surfaces of both bodies. So again, starting with Mercury, the Mercury laser altimeter mapped the surface of the planet at 1064 nanometers wavelength. So on the left of this figure is the Earth-based radar data, and the regions that have an enhanced radar signature are highlighted in black. And these red circles are delineating the rims of different craters. And what you can see on the right of the image is that the laser reflectance has also low albedo that correlates with the Earth-based radar signature. And so what we think is that these water ice deposits are being insulated by a low reflectance material, which is again consistent with an organic-rich volatile, approximately 10 to 20 centimeters thick, on top of the water ice. And what's been really fun to work on is being able to actually see these low reflectance deposits in visible images as well. So I'm going to show an example of part of this campaign where we actually were able to image within the permanently shadowed regions using scattered sunlight from the rims and the walls of different craters. So I'm going to zoom in to Berlioz crater here, which is approximately 30 kilometers across. And again, the rim of this crater is traced here. And you can see at the time this image was acquired, the majority of the floor of the crater was captured in shadow. And so with a broadband filter on the Mercury dual imaging system, we can capture an image of the crater captured in darkness, and it's oversaturated by design. But if you stretch this image, you can actually reveal reflectance differences on the crater's floor. And so as you can see, there's this low albedo deposit And this correlates perfectly with the Earth-based radar data that's collected from the Arecibo Observatory. We also have reflectance measurements of the surface of the moon. So this is a map from a LAMP product where they used far ultraviolet wavelengths to map the surface. And again, the story for the moon is not as clear. This data was used to suggest that perhaps the water ice manifests on the surface of the moon as more of a water frost. And to support this, there was also visible imaging done of the permanently shadowed regions on the moon, and they saw an enhanced signature of the reflectance. So this high reflectance can possibly be explained due to a frost on top of the surface. It's also alternatively been explained by a decreased effectiveness in space weathering. So to summarize these different data sets, both bodies have evidence of radar bright data that suggests water ice is on the surface. However, on the moon, it's always correlated with these regions of permanently shadowed areas that we've mapped, whereas the moon, there's not a one-to-one correlation. On Mercury, the water ice deposits are a lot more pure. They're nearly 100% water, whereas on the moon, we suspect they're only approximately a few weight% water. Both bodies, though, have these permanently shadowed regions that thermally are able to support water ice on geologic timescales. There's also been reflectance and imaging campaigns for both of the poles, and for Mercury, this is consistent with the majority of these water ice deposits being insulated by a thin organic volatile layer, where on the moon they suggest that perhaps the ice is more of a frost abundance. And then finally, I didn't go into this, but Dana touched on it yesterday, is that we also had the L-Cross experiment on the moon where impact into the south pole of the moon suggested that, again, there's few weight% water. So in summary, Mercury's poles have a large amount of water ice, more water ice than we see on the moon, and also they're of a higher purity that we see. And so we're really interested in trying to explain why this could be. And we discussed a number of reasons at the Microsymposium. One thing that came up is perhaps it's due to the different timing of the delivery of the volatiles. So you could imagine that if Mercury's volatiles were delivered in its relatively recent past, that's why they are more pure and extensive, whereas if the moon's volatiles were delivered earlier in its history. We also discussed differences in impactor population, and I think this is something Bill will talk about in his talk following this. But perhaps Mercury has been exposed to more water-rich asteroids as opposed to the moon being exposed to less water-rich meteorite populations. There's also the possibility that there's a difference in volatile abundance within the body itself, and that the volatiles on the surfaces come from planetary outgassing. So if Mercury is more volatile rich, perhaps if the water ice is delivered by planetary outgassing, this can explain the differences. And then finally, this is a schematic from Matt's recent paper, but again, they presented this idea that perhaps the thermal regimes, or the cold traps on the moon, represent a more thermal regime from the ancient past. And then there's everyone's least favorite answer, is that perhaps it's a combination of these processes. So in conclusion, the permanently shadowed regions occur both on the moon and on Mercury, and they're very unique solar system environments. The permanently shadowed regions on Mercury host these pure and extensive water ice deposits that are in higher abundance that we see than on the moon. And many questions remain regarding the source and the evolution of these deposits, and future exploration is warranted to understand these differences. And thank you for listening, and I'm happy to take any questions.
Lucky.
Oh, ha!
We meet again, William.
That was a great summary of all sorts of things going on. I was just going to add a couple other issues, which I was talking in the lunch line with Dana, is that there's also the issue of, like, if you implant water on the moon, it has to hop its way to the cold traps. And there's a certain efficiency of doing that, how much actually gets into the cold trap. Is that efficiency the same on Mercury? Does much more end up being captured because Mercury is a larger body? There's also the issue of that if something hits, how much water escapes into space versus what stays. Are those the same for Mercury and the Moon? So
Yeah.
there's all these things that, we have some models of this, but our models are still kind of in their infancy in terms of all this. And so
Yeah.
it's just more complications, right?
And most of the models only deal with the moon, so
Exactly. Yeah.
Yeah.
So we need Mercury people doing
Yeah.
Mercury things. Right? So,
agreed.
Yeah, something that, as Bill said, great overview.
Thank you.
Something that I'm sure you did not discuss, but maybe at future microsymposiums. It's not necessarily exploration relevant, but certainly science relevant. A paper just recently came out talking about permanently shattered regions on Ceres. And one could imagine that some of the Galilean satellites might similarly have them. Of course, it'd be different because those intrinsically have water. But on the other hand, they might trap even more volatile things. So it might be an interesting sort of, again, future thought about what would you collect in those permanently shattered regions.
So again, good presentation. Thank you.
Thank you.
Question is, you talked about one of the possibilities of impactors, and you mentioned water-rich asteroids. What about sun-grazing comets? Since we have a large population of those, can they contribute? Are they effective at contributing to the water deposition?
Yeah, so comets as well as asteroids are being discussed as that external delivery of the ice. And I think Bill will talk about this.
yeah, you have to come to my talk.
Yeah. But there hasn't been models of this on Mercury, but Bill's going to be talking about that in his following talk.
You mentioned that the water ice deposits on Mercury are beneath the sort of 10 to 20 centimeters sort of layer thickness. But do you know any information about the actual depth of the water ice itself?
Sure. So there are a couple of constraints on the thickness of the ice. So yeah, the insulating layer on top is about 10 to 20 centimeters thick, and that's derived from the neutron spectrometer measurements. For the pure water ice itself, there's a minimum estimate of several meters, and this is due to the radar observations, so they're optically thick at a number of radar wavelengths, and then there's a maximum thickness of several hundred meters, and this is based off a study from Talp et al. In 2012 where they found no statistical significant difference between MLA tracks, or laser altimeter tracks, that went across craters that hosted the water ice and across craters that didn't host the water ice.
And last question.
Yeah, this is a follow-up on the previous comment about the transport. So he's talking about transport of water that's delivered, but the solar wind won't make water on the moon, so it's a production differential, but the temperature gradients on Mercury allow the solar wind to actually be a source term for water on Mercury.
Yeah.
And the distribution of it should be much more homogeneous because of the way it's produced. So that's something else that might be added to the mix.
Yeah, so that's been discussed, and there are a few inconsistencies that have come up with that hypothesis. First is you need a way to explain the low reflectance material that you have insulating those deposits. And then secondly, if you have solar wind interactions occurring over time, you would probably expect the deposits to not be as pure. You would expect more mixing from impacts or a regolith gardening, whereas the radar data indicates that the deposits are very, very pure. So those are also things to think about.
Take your speaker again, please. Okay, we are now about to begin the third and final lightning round session of